Okay, welcome to Chapter 4. In Chapter 4, we're going to be dealing with the concept called probability. And so this is the only chapter really. Actually, Chapter 5 continues with a little bit of probability as well. I apologize for that. But 4 and 5 are going to be dealing with probability, and they're going to lay a good foundation here in 4.1. And so 4.1 is, like I mentioned, the foundation, what we call basic probability. And so let me start with the definition. The probability that an event A will occur is denoted by the symbols P with A in parentheses. Okay, so if you ever see a P in a parenthesis, it's not a times or anything, this is a probability of A. And is found by the probability of A is simply the number of ways A can occur over the total number of possible outcomes. It's that easy. Okay, and so what we want to do is just give you some I don't know, problems right up front to have you practice around with this. Probability is something that can be overcomplicated, so we don't want to overcomplicate it. It has everything for you with you understanding the space that you're in. So let's suppose our first scenario is that we roll a single six-sided die. Okay, let's think about that situation for a minute. And what I'm going to do is tie my questions pretty closely to what they have in the homework for you. So if you're going to roll a single six-sided die, the numbers 1, 2, 3, 4, 5, or 6 could come out. They're going to ask a question like this: what is the probability of rolling a 5? And so what we want to do is simply say, hey, the probability of rolling a 5 is easy. The outcomes are 1, 2, 3, 4, 5, or 6. Those are the possible outcomes with a single roll of a die. Well, that's 6 different outcomes. That's the total number of outcomes that could happen on this one throw. A 1 could come up, a 2 could come up, and we want the probability that a 5 comes up. Well, here's 5. Whoops, that's a little bit big there. Sorry about that. So here's 5 right here. See if I can get it a little tighter. I can't. So 5 is that one number right there. And so the number of ways a 5 could come up is 1. What if we ask this? What's the probability that you roll an odd number? Okay, what if our question changes? Well, we still have 6 outcomes. And which ones are odd? Let's go find them. The ones that are odd, and we'll circle them in red, are 1, 3, and 5. So 3 out of the 6 are red. Sorry, let me go back in there and get the right pen. 3 out of the 6 are red. Now they're going to reduce that in our book to 1/2. So they'll probably ask you to express it as a fraction in lowest terms, and we're going to respect that since a computer is grading it. And so we'll work within whatever bounds they tell us that are there. I'm sorry, I'm trying to move a word problem down that I typed in that I want to refer to later. We're close to referring to that. So far I hope that things are okay. So let's look at a different situation. What about flipping a coin? So we know that a coin has a heads and a tails, and they might ask, with one flip of the coin, what is the probability that we get heads? So it could be basic just like this. And so you never want to complicate it any more than what we're doing. So we think about how you flip a coin. There's two things that could come up, one of which is heads. And so the 1/2 is the probability of getting heads, right? And so you could put the symbols out there or not. Probability of heads is 1/2. Okay. So what you want to notice about probabilities is probabilities are bound between 0 and 1. They can never get any higher than 1. There's no more ways for A to happen than total number of possible outcomes. So it's always a true fraction. But it's possible that A doesn't occur at all. Like in rolling a die, a single six-sided die, what's the probability of rolling a 7? The probability of rolling a 7, well, there are no 7s, and so it's 0. Okay, what's the probability of rolling a number that is less than or equal to 6? Well, that is guaranteed to happen, of 1. And so you can get zeros and ones out, but nothing outside of those. Now, at some point in this section, although they don't use it until the following, they give us some notation. A bar is what they call the complement of A. And so since we're talking here about symbols, I might as well bring it up now. It really means that A does not happen. So remember my first example, roll a six-sided die. What is the probability? Of not rolling a 5. So I'm going to change this, right? I'm going to not roll a 5. Actually, it's just the not that I should underline, right? The rolling a 5 was already there. So in this case, I don't want to get a 5. So let's think about that question, right? Not being the most important word in there. So symbolic wise, this would be the probability of not rolling a 5. And there's 6 options that come out when you roll a die, namely 1, 2, 3, 4, 5, and 6. How many of them are not 5? Well, these 4 are not 5, and that 6 is not a 5, so 5 out of 6 is not a 5, and that's completely reduced, so we would just leave it just like that. So they might throw in that notation in the homework as well, although they'll use it a lot more in the next section. So there we go. There's the complement. Now they're going to ask some questions that get us to really think. And so what I've asked right now is, they call it simple probability, simple event. And they're calling it a simple event. Let me do something really quick here. They call it a simple event because there's not much to it. You roll a die. So let's talk about something that you'll see in the homework. A couple plans to have 3 children. Find the sample space for all the gender sequences and identify the probability of having exactly 2 girls. So they really want to have a majority be girls, and so they're going to have 3, and so they want 2 of them to be the girls, and they just want to know what the probability of that is. So let's talk about the first one, the sample space. So they're having 3 children. The way that we're going to work this is off of the definition. It's the number of ways to have exactly 2 girls over the total number of ways there are to have children, and keeping track of their gender, the total number of gender sequences that are possible. So let's start with a girl on the first birth. If we have a girl on the first birth, then we can have a girl on the second and a girl on the third. Or we could have a boy on the second, and a girl on the third. So this is no boys, 1 boy, but that 1 boy could have been born last with the girl born first. Still a girl born first, we could have a couple of boys. And that seems to exhaust all of the possibilities. So this is the different gender sequences that could take place. We could get a girl on the first birth, girl on the second, girl on the last. No boys. We could have one boy, and that one boy could be second or third if the girl's born first. Or we could have two boys, and obviously that would be second and third. The other thing that could happen is a boy being born first. And so if I do the same thing, boy, 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 let's filter in one girl. And that one girl could be in the last position. And then we have two girls. Those are the different gender sequences that are there. I believe in the homework you're doing it for 4, which is the same as what's in the book. And so, the book homework. And so you want to just take some time to list those out. Be methodical. Notice that I started with all of the one gender and then filtered in one of the other and then 2 and however many you need. So there's 8 different combinations. So when I go to find out the probability of exactly 2 girls, I know my bottom number is 8 because there's 8 different ways to have children keeping track of gender. I know that some of them have the exact same number of boys and girls, but it's different having an older brother than a younger brother, and so they are considered to be different. Now, how many of those reflect 2 girls? Let's go find them. Now, it needs to be exactly, so not the first one because that has 3 girls, but the second one has 2 girls, and the third one has 2 girls. The last one only has 1. And then there's this one right here at the very end. Everything else that's not highlighted has either more or less than 2 girls. And so what am I looking at? I'm looking at 3 combinations out of 8. And that's how I get that probability. And so in some of the questions, you're going to have to create the sample space so that you understand the situation better. So I kept moving down a question. I hope I didn't lose it in that process. I might have, though. Nope, there it is. So let's take a look at this question. I apologize, but it was in the homework, and I wanted to make sure we addressed it. Each of 2 parents has the genotype brown-blue, which consists of the pair of alleles that determines eye color. And each parent contributes one of those alleles to a child. So if I had brown-blue, which I do, I could give my brown to a child or my blue to a child, but I can't give both. My wife has blue as well. I don't know if she has brown, though. She might be a blue-blue. But anyway, if I give off one of my browns, then my kids are going to have brown eye coloring, is what it's about to say. So the first part is that 2 parents come in, and they both have brown-blue eye color alleles. And they can give one of those to a child. And says, assume that if the child has at least one brown allele, that the color will dominate and the child will have brown eyes. So if they have any brown whatsoever, they're going to have brown eyes. List out the different possible outcomes. So as this child gets born, he could get a brown from the mom and a brown from the dad. It could get a brown from the mom, and a blue from the dad. It could get a blue from the mom and a brown from the dad. Or it could get a blue from the mom and a blue from the dad. So the first column, in my way of doing it, I did the mom first and the dad. So if the mom gives brown, the dad also could. But if the mom gives brown, the dad also could give blue. And so that's the first one. The mom could give blue, and then the dad could give brown or blue-blue. So we want to know the probability that the child ends up with brown eye coloring. Well, that's 1. So he's going to have brown if we read this carefully. If the child has at least 1 brown allele. Let's go highlight the ones that have brown alleles. Oops. Sorry, that wasn't the highlighter. Brown has a brown allele. This has a brown allele. And this has a brown allele. So we have 3 out of the 4. So the probability that that child ends up with brown eyes is 3/4. What's the probability that it ends up with blue eyes? The only way for that to happen is if he has no brown alleles, and that only happens in 1 out of the 4 situations. And so you're going to have to, in some of the problems, create these sample spaces so that you understand how to answer the question. And everything's just about you understanding what could happen there. Now, if you look at 3 divided by 4 on a calculator, it comes out to be 0.75. And you'll want to see the decimal points at some point. So somebody could look at this and say, "Whoa, it's super unlikely that they're going to have blue eyes." We don't want you to say that. We have a definition of unlikely. And they're going to ask if things are unlikely to happen. An event is unlikely if the probability of that event happening is less than, and our book puts or equal to, 0.05. So if it has less than a 5% chance of happening, and you can, if you were involved in chapter 1 in the very first section, they use that to tell whether events were significant or not. So take a look at the probability of having blue eyes. The probability of having blue eyes we saw was fraction-wise 1 out of 4. If we put that in our calculator, or maybe we just know it's 0.25, this is not less than 0.05. It's way bigger. It's 5 times as big. And so because the 0.25 is greater than 0.05, so since 0.25, maybe I'll write it like this, is not less than or equal to 0.05, because that's what we're trying to find, is less than or equal to 0.05. So since it's not less than that, having blue eyes, having a blue-eyed, oops, I jumped up from eyed child is not unlikely. It will happen 25% of the time, right? And so we just want you to have that hard and fast thing, so you'll be able to apply that as we go forward. I wanted to make sure you saw a couple of other ideas that came up. One is they describe in the homework and in the book the game of roulette. And what roulette has, it has some numbered slots. And the numbered slots are 1 through 36. All of those numbers are there. And then they also throw in the 0 and the 00. So what I mean 1 through 36, I mean the numbers 1, 2, 3, all the way up to 36 are there, and then 2 additional numbers. They're going to ask a question like this. With 1 spin of the roulette wheel, so it's a big wheel that chooses a number, find the probability that the outcome is 19. Okay, no problem. We want the probability that it's 19. So the first question is how many numbers could theoretically come up? What are the number of numbers? Now, somebody might say, well, one number is going to come up. I just mean what can be in that one numbered position. It could be any of these numbers, anything from 1 to 36 and the 0 and 00. So there are 38 possible numbers that could come up. So as you spin it, any one of 38 numbers could land on. But what do we need it to land on? We need it to land on 19. Well, 19 is just one option out of there. So just with basic probability, we're finished. 1 out of 38. How about this? The probability that the outcome is odd. Well, there's 38 numbers, and how many of them are odd? The person that's not thinking so well will write 19, but it's not 19, because 0 and 00 are neither even nor odd, and so therefore they shouldn't be considered. So the odd numbers are 1, 3, 5, 7, 9, 11, all the way up to 35, following that pattern. How many of them are there? There's 18 of them. 18 out of 38 are odd. There are these odd numbers here. Again, 0 and double 0 are neither even nor odd, and that's why they're put in there. Most casino games, if not all, are not a 50-50 chance. And so if we reduce this, we can pull out a 2 for sure and get 9 over 20, not 20, sorry, 38 divided by 2, 19. Sorry, I don't know why I was thinking wrong. 9 over 19 would be the reduced answer to put in there if they ask for the reduced fraction. If you want to look at it as a decimal, it's 0.474. Now if you're putting answers as a decimal, they follow this rule of 3 significant digits. So 1 out of 38 was 0.0. I don't count the 0, but I start with the first non-zero digit and go out 3. And I'm looking at 0.02631, and so I'm rounding it to 0.0263. And then 9 divided by 19 went forward, and it was what was actually on my calculator was 0.4736, and so I rounded to 0.474. So notice this one that I'm looking at right here, the 0.474, is out to the thousands, where the other one that's circled is to the 10,000s. We're not naming the place, we're just naming the number of significant digits, and it's because probabilities are small. So try to park that in the back of your mind. Notice that that getting an odd number is not unlikely. It happens 47% of the time, way more than 5%. But getting the number 19 out would be an unlikely event, only happening at 0.0263 or 2% of the time. And that's less than 0.05, so therefore it's unusual or unlikely, is the way our book puts it. So you'll see examples like that. The other thing that they have in there is they say something like this: the likelihood, I think likelihood's one word, sorry about that. The likelihood of a thunderstorm is said to be 1 in 24. Express the likelihood as a probability. Well, all we have to do is say, well, the likelihood is 1 in 24. And it's that easy. I just didn't want you to balk at that question. And we get 0.0416 repeating, so I'll put 17. So would it be unlikely to have a thunderstorm? Is an occurrence of a thunderstorm unlikely in terms of this? Yes, because it's less than 0.05. So a thunderstorm is unlikely. I know they didn't ask that, but we might as well follow up, because the probability that it happens, 0.0417, is less than 0.05. You are going to be unlikely if your probability is less than 0.05. So that should help guide you through this section. Hit me up with questions via Canvas as they come up, but hopefully this is a good experience working through this 4.1